that's what it is. Either on get temps, they're supposed to be set temps. Set temp Celsius, yeah. Because yeah. That's what's wrong. Yeah, I actually copied all that over with of each function. So that's on my main file too.
Yeah.
Those also say set instead of check. Yes.
Something you take that.
So really that's not where it's saying the problem is. This in the problem down here somewhere. It's even weirder because it's the right thing that you were calling the wrong thing here, but it was telling you the problem in the right thing.
From one ring and yeah.
All right, you guys ready?
I think so.
All right, you ready for something fun?
Is our pointers fun?
No, they're not fun. They're terrible. But also a lot of fun. I remember when on an evaluation, actually a while ago, I haven't done this recently, but I used to have like former students write letters to current students. So like you guys would come in the first day of class and get letters from last semester's 21 class of like.
I said pointers were horrible.
Right? To say like, oh, this is how you cheat in the class. And, no. But to try to give you a little bit of advice. And they said pointers are your best friend and your worst nightmare. And I thought, that's about right. So they're both. They're really powerful. They're going to allow us to do a lot of cool things and make a lot of cool things in C++. But they have their own complexity to them. They are one of the things that can make your program crash instantly, so that's nice. And things get a little crazy as they get larger. So today, very foundational lecture on what pointers are. We'll build on that on what's today? Today, Wednesday?
Yeah.
We'll build on it on Monday. So when we're all back together on Monday again. And then we're going to get into other stuff that's not necessarily as syntax related. We're going to get into sorting algorithms. We're going to get into linked lists, our first data structure, that kind of stuff. So that stuff's coming. All those things rely on pointers. So pointers are going to be really important. Pointers also are what you're going to use the most on your next coding assignment. That really hard one that I keep talking about. Okay. I won't introduce it till Monday because we need a little bit of this before we look at it and be like, I have no idea how to do this. So I'll introduce that on Monday. But it's going to use pointers, and pointers are not something that you can program the night before and think that everything's going to work perfectly. You can try, but trust me, it doesn't work that way. You don't have any questions? Wasn't that a great speech to get us going? These things are terrible. We're going to have a lot of fun with them. You're going to lose a lot of sleep over them. Doesn't that sound great? I think the hardest thing, maybe not the hardest thing, but right, you've been. What'd you say, Kevin?
I said, joke's on you. I don't sleep.
That's right, exactly. You just work all the time. That's probably true. I mean, you already know this about programming, but programming is really hard to like set how long something's going to take, right? You go home and you think, oh, this lab's going to take me 10 minutes, and it takes me 10 hours, or this lab's going to take me 10 hours, and it ends up taking you 10 minutes, right? Pointers help with that. It takes longer than you think. So make sure you set aside some time to get things going. Or better yet, what? Come to class, come to office hours, right? Get all that going because you can have one tiny little syntax error, not syntax in the sense that it will compile, so I guess technically a logic error, and you won't be able to find it. You'll just be staring at your code over and over and over again. Normally I can find it. Not always, but normally I can find it. Look at all this stuff that we got to do. For those that took my class, I talked a little bit about pointers and algorithms 1. Anyone remember what a pointer is?
It's just pointing to a memory address, right?
Yeah, so it's a variable basically that holds a memory address. So pointers are memory addresses, and so we're getting kind of, right, we think of our programming languages as these high-level languages, right? I don't have to worry about the nitty-gritty, like there's an actual physical computer that uses electricity and a CPU and all that kind of stuff, right? We try to stay above that, right? We leave that for the computer engineers, right? But with pointers, we're going a little bit lower level because we're taking a little bit more control over, okay, really variables get created, they get created in what? Memory, okay? And that has to be carved out somewhere on the machine itself, right? So that location, right, has this relationship with your variable, and pointers allow us to kind of take control of that address and kind of do some cool things with it. So we get a lot more control over the computer's memory. We don't get to decide, right, what memory address our variables get created, but we get to find out what that memory address is, and then we can do some cool things with it. So pointers really hold memory addresses to variables, right? As opposed to actually holding values, right? So we normally think of variables as holding values, right? They hold a 5, they hold the string hello world, they hold the character X, right? Pointers don't hold those things, they hold memory addresses. They say, where is X located? Where is hello world located? Does that make sense? Everyone kind of see the distinction between the two? Right, and they're pointers because they point to the variable. I love the pointer lectures because I get to start drawing on the board, right? Which is good. And I'm just drawing arrows, which I can do. So I really like that as well. I can't draw anything else. Stick people, I can do stick people too. Right? So I think I already said that, right? Variables, where they are as opposed to what they hold. Anyone know where we've seen pointers before? Right, if I say that pointers are all about memory addresses, where have we seen memory addresses before? You just read my slides. Right? You're like, if you're not, that's good. You're on top of it, right? So call by reference, right? We put the ampersand in a parameter, right? And we said that when we pass in an argument, it's not the argument that gets passed in, but what? The memory address of where that argument is, right? That's all done automatically, but it is a pointer. But I don't have to do anything special, right? C++ figures out if I try to put a value into that variable, it actually says, hey, I'm a memory address, follow the memory address to where I need to go. Are we good with that? So that's one place that we've done it. It's basically done automatic, although the ampersand, right, we have to add that in. So that's one way. Where else? I've got one other place. When else have we talked about memory? And like, I got a little lecture on it. Arrays, right? So we talked about it on arrays as well. And we said that arrays hold, right? Maybe we said this, maybe I didn't. Maybe that's why you're looking at me all weird. We said arrays hold the location of the first thing in the array. All right, and so an array variable only knows where the beginning of the array is, and then it adds memory addresses to get where it needs to go, or it goes too far and we fall off the cliff, right? But arrays are all about memory addresses as well. And so those are the two places where we've seen arrays. And so arrays and array variables and array parameters, they hold the location of the first element in the array. So they don't hold the array, they hold the location of the first element of the array. Location is just synonymous with what? Memory address, right? Location, memory address, read those two things, that's the same thing. Now they're all handled automatically for us, right? I say that, but there is special syntax we use, right? Call by reference, we have the ampersands. Arrays, what special syntax do we use with arrays? Square brackets, good, right? See if I make my hand square. I don't know. Square brackets, right? So it's handled automatically, but we do have to do something to make that automatic stuff happen, okay? So today we're going to kind of decompose those and also add in more operators, now that we know what operators are, right? More operators to work with these memory addresses. Good? So pointers basically are stored in variables, so we're going to create variables. And the variables have a special type, it's a pointer type, all right? And the fun thing is that every type that we know can be a pointer type. So we know integers, you can have an integer pointer. We know doubles, you can have a double pointer. We know strings, you can have a string pointer. If I created money, I could have a money pointer, all right? Money tree, that sounds pretty good. Maybe that's at the end, we're gonna do trees at the end of the semester. Okay. It's pretty easy to do. We just add a star on the identifier, right? So to create a pointer of any type, you just use the type that you want to do and you add a star. Technically that star floats. So everyone see the star, it's on the P. You'll see syntax where it says double star space P. You'll also see syntax where people can't make the decision to go double space star space P. So it has to be somewhere in between and you're good. I put it on the identifier. I recommend you put it on the identifier to, when you look at the variable, you automatically see that it's a what? A pointer, okay? Which means P does not hold doubles. What does it hold? Memory address, and more specifically, what? Memory addresses of doubles. Okay, so there's this higher level info with a double pointer that says, not only do I point to a variable, but the type of the variable that I'm pointing to is a double, so we can interpret the values appropriately. So double pointers point to doubles, integer pointers point to integers. Integer pointers don't point to strings or doubles or anything. Right? Just like before, right? Types point to the right thing. So that's what that says. So here's a lovely example. It's kind of fun. You can declare them inline. Right? So how many variables did I create?
4.
It's not a trick question. Good. I see 4 things. I created 4 variables. Right? But the types of the variables are different. Right? P1 and P2 are
Pointers.
Pointers that point to
Integers.
integers, and V1 and V2 are
Variable.
whatever you said. Yeah. That sounds
They're just integer variables.
right. They're just plain old boring integer variables. Don't you love that when you're in coding classes, all variables are integers, right? We rarely talk about either ones, right? It's only 3 letters, so that makes it really easy. They're whole numbers, that makes it really easy. I don't have to come up with decimal points or anything. So these are integers, but they're not integers, they're int stars. Right? Meaning that they're pointers to integers. So what I never write on the board when I talk about variables is the fact that every variable has to be located somewhere in memory in the computer. Okay? The compiler, the operating system, they're in charge of making sure that variables get allocated correctly. Right? When you run your program, variables get created in memory somewhere in the computer. Everyone good with that concept? Happens automatically though, that's great. They're normally hexadecimal, or they are hexadecimal. So I'm just gonna make up where these might be. They won't be 0x1 and 0x2. Partly because, right, integer variables take up a byte, or 2 bytes, or 4 bytes, right? So they're gonna take up space, but we're just gonna make it easy. So every variable you create, whether it's a pointer variable or a regular variable, has a memory address associated with it. You don't need to know what it is, right? But you need to know how to kind of link them together. So my V variables, what do they hold?
Integers.
Integers. So they hold things like what? 5 and 10. Everyone good with that?
Mm-hmm.
What do my P variables hold?
The hexadecimal.
The hexadecimal, right? Memory addresses of variables, right? So what values based on the board could I put in P1?
0x1.
0x1 or
0x2.
0x2. Any more?
No.
No. Because 0x3 is of type what? Int star. So an int star, right, an int pointer points to integers. If you want to point to an integer pointer, you need an integer pointer. Really, int 2 stars. 2 stars point to 1 star, 1 star points to no stars can't point. You always lose the star as you point. So this could be 0x1. And this could be 0x2. Everyone go with that idea? So my pointers hold the memory addresses of my variables.
You see out that you'll get the LX1.
Yeah, but I see out P1, I get 0x1.
How do you know where the hexadecimal of that integer is?
You don't.
Yeah, that's what I was saying.
Although we're gonna talk about it, but this lovely thing will tell us. My ampersand's not.
Oh, that's an ampersand. I thought that was some sort of
Come on!
I thought that was like an L that was on
When I first
steroids.
started teaching, I couldn't even draw an ampersand. So This is after like 8 years of teaching. I can now somewhat draw a name.
LS right there.
It's not something you write, ever.
You have a point at pointers?
What?
Is it a thing to point at pointers?
Yes, it is. And in fact, your assignment that I this doom and gloom assignment, you'll do that. And there's a really important reason why, but we'll get there. Right now, pointers seem really easy, right?
No.
I hope. No, they don't already. I mean, it's pretty basic. It's just a memory address that points to a variable.
It's not that hard.
Not that hard.
Variables with extra steps.
Yeah, exactly. It's like I taught you the easy way, and now I'm teaching you the harder way. Right? And we're gonna figure out why we need them at all. All right, we know that. Yeah, blah blah blah. Right? The way to talk about pointers, you have to be very precise in your language, because otherwise, what you say and what's happening become two different things. So if P1 holds the memory address of V1, which it does, right? Everyone good? P1 holds the memory address of V1. Then we say P1 points to V1, okay? And a lot of times you'll see me draw it, because eventually I don't really care what the memory address is, I just care where it's pointing. I remember I said I gotta draw today, right? So P1 points to V1 because P1 holds the memory address of V1. And the same way, P2 what?
Points to V2?
Points to V2.
Couldn't you just say P1 equals ampersand V1, and then that's where the hexadecimal is stored?
Yes.
Okay.
But eventually we're going to take out the name of the variable, and that's where we're going. But yes, the ampersand gives me the address. So, right, Denzel said, can't I just do this? And the answer is yes, you can. You can say P1 gets assigned the what? Memory address, read the ampersand as the memory address. P1 gets assigned the memory address of V1. Or in essence, P1 points to V1, right? P1 gets the memory address of where V1 is located. So it now points to it. So we can link these together in a way. Right? So now, there's really two ways to get to V1, right? The plain old normal way where we just do V1. And you're like, why would we ever do it a different way? And you wouldn't actually, but this helps set up what we're trying to do. Right? Or, right, how else can I say it? Not just V1, but the right, star P1, the variable pointed to by P1. We'll add the star, the dereferencing in a second. Right? So when we say the variable pointed to by P1, we put stars in front of the variable to dereference it. And that just says that we're not going to this variable, we're going to what this variable is pointing to. Very verbose, right? So that's the dereferencing operator. So the star not only creates pointer variables, that's on creation, on declaration. Later on, it becomes the dereferencing operator, and it says the variable pointed to by this variable. Does that make a little bit of sense? Or the star is also what? It's just multiplication, right? So the star, you'll notice, right, the compiler has to read it in context, right? What does this star mean? Is this create a pointer? Is this dereference a pointer? Or is this just multiply a value? Does that make sense? Right? And so the compiler has to do that, which means you have to what? You have to do that too, right? You got to figure out the context. What am I trying to do? Declaration is not hard, right? I'm creating a variable, the star in there, that's not hard. Oh, back to this example, right? We're going to say that we have something like this. Right? I technically don't have this yet. Right. If star P1 V1 creates me a pointer and creates me a regular variable. They both get memory addresses, right, assigned by the computer. When I say V1 equals 0, that should be easy, right? 0 goes into
V1.
V1. This says what? How would I say that in English? P1 gets the memory address of V1, right? P1 gets assigned the value memory address of V1. So P1 gets what value?
0x1.
0x1. In essence, it what?
Points.
It points to that. Something new, right? Star P1 gets assigned 42. Where does 42 go? In the V1, because
It's pointing.
it's pointing that way, right? Star P1 could put it somewhere else if it was pointing somewhere else, but right now it's pointing to V1, and so V1's value becomes
42.
42. So when I see out V1, what do I get?
42.
When I see out star P1, I get?
42.
You guys are rock stars. Right?
Just
When we learned about pointers in programming one, I never really used them in assignments unless it was required because I guess never really.
Yeah, we didn't get deep in that last semester.
But how do programmers often, like professional programmers, do they often like use pointers? Or?
Yes, they pretty much only use pointers. And we're gonna get to why. Right, it all has to do with dynamic stuff.
So if you do star P1 equals 42, and then change where P1 is pointing underneath of it, will it put 42 in wherever you change the pointer to?
No, so if I had like V2, right? And then I had said, right, this arrow actually points to here. 42 would still stay in the original variable. Right, it won't copy the value.
does the pointer have more precedence than the variable? So if you just say v1 equals 42 and then try to change it again by assigning the pointer to a different value, does that have more precedence over the variable changing?
No, it's all the same. So
It's all-
whatever comes first.
Okay.
But the thing with pointers is that you have to know where they're pointing to, right? Otherwise, you're screwed. Like, you have to remember. And C++ isn't going to tell you, oh yeah, this is pointing here and that's pointing there. All right. From our previous example, which was this, I think we're going to create this v2 variable. Let's get rid of it for a second. All right. We have P1 pointing to P1, or sorry, P1 pointing to V1. I can also say int star P2. All right. It's an int star, right? It has its own memory address. Right? Okay. Something new. What happens here?
P2 gets the memory address.
Yeah.
P2 gets the memory address that P1 has, okay? So this is key. Okay, this is assignment of pointers. What we try to say is that P2 points to P1. All right, a lot of times that's what our brain's going to tell us. P2 points to P1. Right? Which is saying P2 points to what? P1. Is that what's happening?
No.
No. Okay, what does the equal sign mean? What's the name of it? Assignment, right? So let's talk about this. All right, this should help us. If I have X and it's 5 and I have Y and it has no value, right? When I say Y equals X, I said equals, I shouldn't say equals, right? Y gets assigned the value of X. What's going to happen?
Y is 5.
Y gets 5. Okay? In the same way, when I say P2 gets assigned P1, P2's box is going to get the value in what? P1's box. Does that make sense?
Yes.
So it gets 0x 1, which means that it points to where?
v1. Ah.
You see the difference? P2 does not point to P1. Ready for it? P2 points to the variable that P1 is
Pointing to.
pointing to. I have no idea how many times I just said point, but it's a lot. Right? P2 points to the same place P1 is pointing to.
Ah.
P2 gets P1's value, because that's what assignment says. It says whatever value is in this variable, right side, that's what gets assigned to the variable on the left side. Everyone good with that? So when I see how star P2, what do we get?
42.
Beautiful. Okay, now I say don't confuse these two things, so let's confuse them and see what happens. Get rid of some arrows for now. We get a variable v2 whose value is 5. Any questions on these 4 lines and what I did? create 4 variables, 2 are pointers, 2 are regular integers, and then I just assign those regular integers integer values, right? We've been doing that since last year, so we should be good with that, right? And then the new syntax, P1 gets ampersand V1, P1 points to what? V1, and P2 points to V2, right? And just to put home the point, this is V1, but now it's also star P1, right? That's the name of the variable currently. This variable is V2, and it's also
Star P2.
star P2, right? I have 2 ways of accessing these variables, right? Those are the 2 ways, so those are basically their 2 names. And now I say don't confuse P1 gets assigned P2 with star P1 gets assigned star P2. All right, P1 gets assigned P2, that's assignment of what?
Memory addresses?
Memory addresses. So what is it going to do to my arrows?
Points in the same direction.
Points in the same direction, right? It's going to move them. When I'm assigning memory addresses, arrows are going to change. Okay? In this case, we say P1 gets assigned the value of P2. Well, what is the value of P2? I didn't put a value in there, right? But the value is the what?
The memory address of
The
V2.
memory address, right? The arrow. Let's call it that, right? So P2's value is the arrow, and so we're going to take P2's arrow and store it into P1, which means P2's arrow, which points to V2, P1's arrow is now going to point to V2. All right, going to take a detour. Go down this one. Which means the name of this variable is no longer star P1,
Star P2 now.
right? But this variable is also now what? Star P1. 3 ways to get to the same variable,
Oh,
right?
jeez.
P2, the variable pointed to by P1, and the variable pointed to by P2. Like 3 different. Which you should never have. So when I do assignment of pointers, I am changing the arrows, right? Because I'm assigning memory addresses. That's key. Okay, let's look at where we were before. Right, and let's do the stars. Star P1 gets assigned star P2. What does that do?
It's changing the variable, right?
V1 gets the value of V2, right? Because the variable pointed to by P1, the variable pointed to by P1 gets the value of the variable pointed to by P2, right? So V1's value gets what? 5. So you notice 1 was assignment of memory addresses, meaning the arrows are going to change. 1 was assignment of the variables they are pointing to, so you just change the values, right? That's what we're used to, right? But don't confuse them, right? When you work with stars, you're working with the values of the variables. When you're working without stars, you're working with the pointers to the variables, right? It's a big key distinction. Questions there? All right, let's write a little bit of code. Let's see what happens. Pointers are built in, right? They are a key feature of C++. Right, so we say star P1, comma star P2. Remember, that's not dereferencing, right? That's creation of pointers. We do int v1 equals 1, v2 equals 2. Right, then we say P1 gets assigned ampersand v1, and P2 gets assigned ampersand v2. Right, that's what we just did on the board. Right? But if we see out, right, V1 and we see out a space and we see out star P1, what's my expectation?
It'd be the same thing, right?
Same thing, right? Because P1 points to V1. So it'd be the same thing in this case, should be value of
1.
1, right? Value of 1.
Is the pointer pointing garbage on declaration?
Ooh, great question. Yes. So Pointers, just like any other variable, start with garbage, right? So instead of being a garbage integer value, it's a garbage memory address value, which is usually worse. Because now it's pointing to some place in memory that probably you don't have access to, which probably will crash your program. So we both got ones, right? That's good. Let's change this up. Let's do ampersand v1, and let's output just p1. Okay, what are we outputting now?
Memory address.
Memory addresses. So we actually get to see where in memory v1's located. Right, that's what it's saying. Where in memory is v1 located? All right, and it's located there. You can see why I just put 0x1 and 0x2 on the board. Right?
It actually shows us.
Actually shows us, yeah. My computer's got a lot of memory. I'm not bragging or anything, but those are long memory addresses because my computer's got what I consider a lot of memory, and you're probably like, yeah, I've got like 8 or 16 gigs. Right? That's like nothing.
That's a lot. That is a lot of memory. For a program, yeah.
Yeah, I don't need that much for what I do.
Mine.
Those all match, agreed? Right? It's kind of fun. You can also look at the memory address of that. Let's output all the memory addresses.
Gonna write a for loop.
No for loop. Ampersand v2 space ampersand p2. Right. What do you notice about the memory addresses?
They're pretty close together, right? Like the numbers.
They're pretty close together. Remember, the ones on the left are integers and the ones on the right are pointers. Right? So you'll notice that each integer takes up how many bytes it looks like? 4, right? Because it goes 27, don't look at all the numbers, right? It just goes 270 to 274, right? 4 bytes, right? And the next variable, the pointer's looking at 278. So the first 2 integers got placed in sequential memory, right? 4 bytes away from each other. Make sense? Notice how much does the pointers take up? 2 bytes, right? So the memory address, because it's long, is 2 bytes long. Sometimes they're 1 byte long. Here it's 2 byte long. Right? The integer is 4 bytes long. Right? Doubles are longer than that, right? A lot of times 8 bytes. Right? Strings can be longer than that. Right? So correlation between regular variables and pointers, what correlation are you getting? Pointers are
Smaller?
smaller, not even just half, right? They're half for integers, but they're going to be smaller. They're always going to be smaller. All right? Which is why call by reference we say it's more efficient, because they're small. Right? That's going to come back, and there's a reason why we use pointers, and part of that is because, right, we don't have to allocate things that are as large right off the get-go.
Makes the program run a little bit faster.
Yeah, right? We're not using as much memory. We're not Chrome. We're not going to take all the available memory.
Yeah, Chrome sucks. It just takes like 8 gigabytes of RAM.
If you let it, it will eat up all the memory in your computer. And maybe because I have like 80 tabs open, but you know, I want to have 80 tabs.
That's why I don't use Chrome anymore.
Is the memory address that tells you to the first location?
Yeah. So that's why C++, that's why it's strongly typed where we have to say it's an integer, it's a double, because that means something to the program. And so because it knows the variable is an integer and I try to output it, it says, okay, here's the integer, this is where it starts, and we know integers are 4 bytes. And it knows how to interpret, because bytes, we're just talking about ones and zeros, right? So it knows how to interpret those ones and zeros as something. Anyone taking architecture right now? CSCI 10? Yeah. So have you done like two's complement and that stuff yet? Yeah, so you understand more of what I'm talking about.
All about chunking.
Mm-hmm. That's how you do loops and functions. Anyways, so when you we're not going that low, but right, that's how, right? If you're interested in that kind of stuff, we do have a class that teaches that stuff. Other questions? It's kind of cool, right? It's a totally different way of kind of looking at our program, looking at, oh, it actually runs on a computer in memory, right? Ones and zeros actually get interpreted on the CPU. Sometimes we, as programmers, we kind of like forget about the fact that we run our programs on computers. It just works, right? We just compile it. It all works, it runs. That kind of stuff. But things have to be allocated, so on and so forth. All right, you ready for something new?
Yeah, new operator.
Yeah, the new operator, right? That's good. That's my bad segue into what we're gonna talk about. So you would never do this, okay? So I just wasted the last half an hour plus of your life, okay?
Oh.
Never do this. We're talking about 2 bytes versus 4 bytes, right? So when you're working with plain old data, you would never really use pointers because it's just more overhead. Right? And when I say plain old data types, I mean small things like integers, doubles, chars, booleans, those 4 things. The things that always start with garbage, right? The plain old data, right? Notice I did not say what. What's the other thing that we use a lot?
Strings.
Strings. Strings are classes, right? So they make objects which are large. All right, so they're not plain old data types. Okay. Let's talk about new and then talk about why we create things and go on from there. So pointers can point to variables that have no identifier, meaning they have no name. Right now I create a variable that has a name. It's v1, it's v2, it's right, whatever it may be. To create and allocate memory without a name, all right, we can use an operator called new. Remember I said operators are symbols that do stuff? Except for new, new's an operator, and it's not symbols, right? It's actually a word. It's just a couple that are words, right? And so these variables we create are nameless, so the only way that I can access them is via a pointer, because they don't have names. So the only way I can access them is by storing the memory address of where it's located in a pointer, and then dereferencing it. Syntax is not hard. Int star p1 creates me a pointer variable that can point to what? Integers. And then I can say p1 gets assigned new int. New int creates, all right, I'm going to say allocates, because that's the words that we'll use. It allocates an integer variable, okay, and also returns the value or the memory address of where that variable was allocated. Right? So new int creates an integer and also becomes that memory address of where that variable is. And then we store that memory address in what? A pointer. Everyone good? This int and that int need to match. Right? It could be double star P1, P1 equals new double. String star P1, right? P1 equals new string. You can also do it on one line. Int star P1 equals new int. Right? You can declare and allocate, right? Just like we're used to doing with regular variables. All right, so I think I have a better slide. Here we go.
I know it says nameless, but it has a name.
Well, it doesn't have a name, right?
Well, it's just a pointer, right?
Right, but the pointer can have any name, and any pointer can point to it. So
Yeah.
the name can change, like shapeshifters, the variable name shifters. Okay, what does this do?
Creates a pointer.
Creates a pointer, yay! P1. Of type what?
Int star.
Good, answer. All right, this does 2 things, right? In an assignment statement, we always work on what side of the assignment statement first.
The right.
Good. So the right says create me a what? A new int. A memory space that holds an int, right? Later on, we'll learn that where that comes from is different from where all my other variables come from. Okay, but this is kind of cool. Usually, your variables are created when your program starts, right? At runtime, right? You compile it, which sets up all your code. When you run your program, all your variables get allocated. They all get allocated together, which is why in our last example, we saw that all the memory addresses were next to each other. Does that make sense? Right? This doesn't happen when the program starts. Okay, new int happens when it happens in code. First line, 8th line, 1000th line, right? It allocates memory for a variable, but it does it differently than our regular variables. Does that make sense a little bit? And so I get this new integer, and not only do I get a new integer, it becomes the memory address, right? So if this was 0x1, right, what new int becomes is what? 0x1. What am I doing with the 0x1? Storing it into P1, right? So it becomes 0x1, but in essence, what are we saying?
Pointing.
Good, right? In essence, we're saying P1 points to a new integer. variable. Which makes the name of this nameless variable be what?
Star P1.
It's nameless, but it has a name. So when I say cin star P1, that says what? Ask the user for a value, store it into the variable pointed to by P1. So give me a value.
7.
I think I heard 7. What about this? Star P1 gets assigned star P1 plus 7. I know it looks ugly, but what is it doing?
Just adding 7 to the integer?
Right, exactly. Work on this side first. Star P1, the variable pointed to by P1, whose value is?
7.
7. What are we going to do to it? Add 7, so it becomes, and then we're going to store it into the variable pointed to by P1. And so the variable pointed to by P1, which is this one, becomes
14.
And when I see out it, what do I get?
14.
14.
That just saves like a couple bytes. The whole process?
Well, this one actually eats up 2 extra bytes.
Oh. We could just create
Because your integer is still 4 bytes,
Yeah.
right? This is still 4 bytes. This is 2 bytes in my implementation, right? 4 bytes, 2 bytes. So when I just create an integer variable, it would take up how many bytes? 4. When I create a pointer on top of it,
It's 2.
2. 4 plus 2 is 6. So I wasted 2 bytes.
I see.
I told you don't do this, right? Everyone good with that? I said don't point pointers to, right, regular variables. Okay, it takes up 6 bytes, but it doesn't take up the 6 bytes until what?
For runtime, right?
Not even just runtime, but somewhere in the middle of runtime, when it gets there, right? So when I get to new int, that's when it's going to take up the extra.
So theoretically, if you only had like, let's just say your program needs like, I don't know, like a kilobyte of memory,
Mm-hmm.
and then you add more memory like this, will it just crash?
Mm-hmm.
Oh,
Good for us that our computers have
gigabytes.
gigabytes of memory. We're not really that worried. Yes. Yes. But today doesn't feel like a destruction type day. We're gonna do that on Monday. Right now we're just gonna create. Today's like, you know,
Is there ever going to be an
it
assignment?
is exactly a memory leak. Okay, so let's talk about these variables. These variables that are nameless, we call them dynamic variables. They're dynamic because they get created and eventually destroyed at runtime.
Okay.
Does that make sense? So they get created and destroyed at runtime.
Like during
Runtime, yeah. Not at the start of runtime. Sometime during the program, right? How about this? While the program is running. There you go.
So is this the concept of like memory dumping?
No, memory dump is a little bit different. Memory dumping is like dumping all the hexadecimal of all the memory and then going through it and figuring out, okay. Because you can kind of figure out, okay, if I knew an integer was at this location, I knew your password was at this location stored as a string, then maybe I could figure out what it was.
Uh-oh.
That's not this class. Take the security class. Look, I'm telling you about all these other wonderful classes that we have on campus. You want to hack something? Take this CSCI 17 security class. You want to know how bits move and shift and do weird things? Take the CSCI 10 class.
That's not assembly?
That is assembly.
Yeah.
They call it computer architecture and organization. Because not only are you learning assembly, you're also learning like the architecture behind it.
Yeah.
Yeah. Yeah, it's a lot of fun, right? I haven't used assembly since I was in college. It's good though. It's good to know what's going on. Oh, we should look at one example. Okay. All right, let's see what's going on. Create a pointer. Point the pointer to a new integer. Right, that new integer is unnamed, but you can point to it via pointer, which is why on line 14 I say what? Star pointer equals 42. So when I output star pointer, it's going to output what? 42. When I put pointer, it's gonna put what?
The hexadecimal?
A hexadecimal memory address. Do I know what the memory address is?
No.
No. Do I care?
No.
No, I just care that that memory address is the memory address of my nameless variable, right? That's all I care about. But I don't care what the value is. Hey, look. Another star, right? Int star P2, what does that create?
Pointer.
Another pointer. Now I assign it a different pointer, so it's assignment of
Pointers.
memory addresses. Good, pointers, memory addresses, which means that am I changing arrows or am I changing what the arrows are pointing to? Maybe those are the same thing. I don't know. Right? What does that say? What does that line say? P2
Guess the memory address of pointer?
gets the memory address stored in pointer
Yes.
as opposed to of pointer, right? We want to make that distinction. P2 is not pointing to pointer, it's pointing to what pointer is
Pointing to.
pointing to. Right?
We need an ampersand for pointing into.
Here, no.
The new variable. gets
Because
the address of-
I basically have this, if this is pointer, and this is the nameless, right? Now I get P2, right? P2, which is an int star, right, gets the value in P1.
I meant to point at P1.
Oh, yeah. If you wanted to point it at P1, you would have to say ampersand P1, and this would have to be
2 stars.
2 stars. Because two stars point to 1 star points to no stars, and no stars are boring because we have stars. This just shows that, okay, and star P2, which is this variable, is a what type variable?
Integer.
It's an integer, which means that you can do to that integer anything that you could do to any integer variable. Let me say that again. It's an integer variable, so whatever you've been doing with integer variables all semester long, you can still do with this one. It's just star P2 as opposed to V2. So I can take that value and I can store it into a regular integer because guess what? Star P2 is a
82.
integer. It's a regular integer. But because it was created dynamically while the program was running, it doesn't have a name. The only way to get to it is via a pointer. Questions there? So now I've wasted almost all of our time, and I taught you absolutely nothing that you would actually use.
Ah.
But let's get to something that you will use. So array variables contain the memory address of the array, right? We said that at the beginning of class, right? Which means that if memory addresses are pointers, then array variables are also pointers, right? Connect the dots, right? Remember when you would do that and you'd say like, right, therefore, remember that symbol? Right? Just do it the logic. No, you don't remember that symbol?
Never did that.
Anyone take logic? That's like the one GE class that you should take.
I took philosophy.
No, like philosophy logic.
Yeah, I took that.
Yeah.
Oh,
So
yeah,
what do we do
yeah.
as programmers? Everything we do is logic based, right?
Yeah, I think I do actually remember that symbol now.
You'll do logic in discrete. I don't think you guys are there yet. Right? Discrete's this inverted class right now where the hardest concepts at the beginning and then the easiest concepts. You're to logic. Yeah, see, so logic's very important as programmers. Because computers do exactly what you
What you tell them to do.
to do, right? And so if your logic is faulty, guess what the computer's logic is going to be? Faulty. All right, so let's look at this. Right? Remember, this semester is also about, we lied to you last semester, or whenever you took other programming classes. And so now that you're adults, kind of, right? I can say I'm not actually lying to you. It's like when you tell kids that they can't go into the pool after they eat, right? Maybe your parents told you that. You can. There's nothing wrong with that. They just didn't want you to.
No.
Mind blown this morning. Good. I think they just didn't want you to throw up in the pool because that's embarrassing. But there's nothing scientifically a reason why. So when I said int A3, that creates me a what?
Memory address, right?
Well, let's not go deep yet. Let's go before today's class. What would you have said? Creates me
An array.
an array of size of integers, good, of size
4.
right? And I would draw it like this, agreed? That look familiar? Okay, but today we said that array variables are what? Pointers. So they're not arrays, they point to addresses, where the array is. So this array of integers, okay, is not A. A is a what? A pointer that points to the beginning
Oh.
of my array. Which means A is of what type?
Int star?
Good, it's a pointer, so it would be int star. Did we have to know that before today? No. Right? Because we just said it worked, and with the square brackets, it works just fine. But A is technically an integer pointer that points to the first memory address of your array. So this is what arrays actually look like. Right? So if this isn't the array, right, the two together become my array. So if I say int star p, that creates a variable called p whose type is what?
Int star?
Int star. Which looks a lot like A, whose type is int star. Right?
Ah.
And so you can do things like this. You can say p gets assigned A. This is an assignment of what?
Pointers.
Memory addresses. Good. So p gets the value of A. Well, the value of A is this arrow. Agreed? And so p, right? We can put it from different directions, but it's all the same, right? It's pointing to the first element of my array.
You can just change the name of the array all the time.
Yeah, sure, why not?
It'll be the same array.
So you can now do p bracket 0, p bracket 1. Well, you can say p bracket 1, right, gets a 5. Go to p, add one memory address location, right, and you put a 5 there. So what do the square brackets do? They do two things. To follow an arrow, what do we have to do? What? So find the location, right? And how do I get down the arrow? What have I been using? What character? The star, which is called the dereferencing operator, right? So the square brackets dereference. Okay, everyone got that? The square brackets dereference, but they also add memory addresses, right? Because when I say p bracket 1, I'm saying basically go to the second element of the array, right? But really what I'm saying is add 1, right? Go 1 down in the array. Does that make sense?
Or 4 bytes, right?
Yeah,
Right.
if it's
Okay, so 4 bytes if it's a what kind of array?
an integer.
Right? 8 bytes if it's a double, however many bytes if it's a string. And it'll know that, which is cool. So a dereference is basically the square brackets say go down the arrow and then also add memory addresses. Right? Which is kind of cool. You can do this. You can say star p plus 1. That does the exact same thing. We haven't gotten into adding memory addresses, but if you add integers to memory addresses, it doesn't actually add an integer to it. It adds a memory address of what it is to it. So it'll move you down 4 bytes, 8 bytes, however many bytes it needs to be. And then you dereference it. So these two things mean the same thing. And you can see why we added square brackets. I say we, but obviously it wasn't me. But square brackets got added because the other syntax is ugly. Good? So A and P can both be pointer variables, but I say you cannot change the pointer value in the array variable, meaning that this arrow is dedicated to this array. You can't change the value of A, but you can point P to the same place that A goes. So you can't do this. Okay, you guys are smart. If I said that you can't do that, what does that tell you about this variable? No, not precedence. Oh, there you go, right? It's really not an int, but a what? It's a constant. Right? You can't change it, it's read-only, right? So once again, when you create an array, not only is it creating a pointer, but it's making the pointer constant. And that's important because what would happen if you pointed that arrow, let's say this didn't exist, if you pointed that arrow somewhere else, what's gonna happen? Use block of unused memory, right? That's called a memory leak, right? or we call it orphan memory because it gets left over. It's kind of sad. It's a terrible name for it, but that's the name that they use it, right? Because it's been left, okay? You can't get back to it. Okay, in C++, once you no longer have a pointer to a memory address,
It's gone.
a nameless memory address, it's gone.
I mean, it's still there, but
It's
it's
still
gone.
there, but you don't know how to get back to it.
It's like having a house, but just removing it off of the map.
Exactly.
But it's still there.
It's still there, it still exists.
It's like
If you were
talking-
able to find it, it would be there, but you can't get there.
Yeah.
You can't point to a specific address if you don't know the address. So I can get to your house if you tell me your address, but when I forget your address, then I don't know how to get to your house. But does your house still exist?
Yeah.
Yeah, it still exists. I just don't know how to get there. Does that make sense a little bit? We're gonna make lots of memory leaks. That sounds like fun. All right, so those are regular arrays. Great. Let's get to something that is good, and those are dynamic arrays. So dynamic arrays are like dynamic variables. So when I say dynamic, I mean that they're created when? At runtime, when you're ready to do it. And I have to use what? New. Okay, so that's key. Anytime I say dynamic, in your head you should think new. Dynamic things get created with the operator new. Okay? So you can create dynamic variables, but we said that's kind of ridiculous. There's no point in doing it. But you can create dynamic arrays. When I created my array, I got a pointer and I got this memory. Everyone good with that? Okay. I could do that at runtime. Okay. And this allows me to create arrays of any size I want while the program is running. Right now, you determine the size of your array at not runtime, but compile time, right? I have to say int a bracket 3, right? Create an array of size 3. And we said you can't create it at runtime. You can't create it from variables, let's say inputted from a user. Okay? Well, you can once you get into dynamic. So let's look at this. So here's a size variable of size 3, right? This might be the last thing I draw. We'll see. You're loving my drawings though, right?
Yeah.
Yeah, thank you. All right. So size variable is 3. Right? Oh, look, I didn't do an int for once. I get an array variable, although that's misnamed, right? Did I create an array?
No.
No, I just created a double pointer. Right?
Double star.
Double star. That sounds pretty cool.
There's no triple stars yet.
All right, double star. Okay, let's go back to my last example a little bit. I told you I'd draw some more. So here's A, it was int star, and it pointed to an array of size 3. Everyone good with that? I also, earlier in the class, had P1, which was of type int star, right? And it pointed to just a regular integer. Is that my timer? I've talked too long. Should stop. Okay. What do you notice about these two things?
They're kind of the same, right?
They're kind of the same, right? Basically, if I cover up this part of it, are they the same?
Yeah.
Right? They both are just of type what?
Int star.
Int star. But they can point to an what? Array or an integer, okay? So a pointer variable can point to just a regular variable, or it can point to an array of variables, okay? But it's not, you don't change the pointer, it's still just a pointer. So a double star pointer can point to a single double, or an what?
An array of doubles.
An array of doubles. And it's the same syntax, okay, as far as creating the pointer. The syntax to create the thing, the dynamic thing, changes, and not by much. Right? If I just wanted to create a regular variable, I would have said array equals new double. Agreed? But now I say new double square bracket how big I want the array to be, and it will create me an array of that size. So new double bracket size says create me a new double array of size what?
3.
3, because size is
3. And you can always change size.
You can always change size when you create it. You can't change size after it's been created. And that becomes the memory address of the first thing in my array. And so my array pointer points to the first thing in the array. Now here's the beauty about dynamic arrays. You ready for it? Once you create a dynamic array, it's just a what? Just an array. Which means everything that you already knew about arrays holds. So don't throw all that out. You want to put a value, right? If I wanted to put 10 right here, what would be the syntax?
It was array 2.
Array,
Bracket 2
bracket 2.
equals 10.
Am I good with that? Because once you create the dynamic array, it's just an array. And so you just do everything that you already know how to do with arrays that you did in your first assignment, right? You can now do with the dynamic array. What makes it cool? You can create the size at runtime. So you can ask a user how many scores they want to input. You can ask a user, right, how large they want this thing to be, and then you can create it to be that size. Before it was like, well, maybe the user will type in 100 things, so let's make it a size 100, even though the array maybe only was going to hold 3 things, right? Let's just make it large enough and hope for the best, right? Now you can make it as large as you need it to be. I think that's everything that we just do. Some notes, right? The pointer needs to be of the base type of the array. So if the array, look at this. That's not int. What is that supposed to be?
Double. What would happen if you? No, never mind.
Compile it.
Yeah.
Because the types don't match. Int stars can't point to doubles. Pointer double star, base type double, right? They just need to match.
Can doubles point to floats? Or vice versa? No?
Because they're different size.
Yeah.
You need to dedicate it to the array. So notice this, I didn't make it a const double, although you could. But this needs to be dedicated to that array. Right? Don't point that somewhere else, or what's happened? Orphan your memory, which is bad. Really bad. Bless you. Thank you. All right, let's make something. That is something that maybe you actually would do. So I'm going to say int size. I'm going to say string star students. All right, create a single integer variable and create a pointer that can point to either a string or what? An array of strings. Right? It could be either. And I don't really care what it is, right? That's all I use. So see how many students. All right. C in the size. I'm going to use get line, so I'm going to need to do an ignore. All right. Here's the good enough, right? 1,000 characters should be enough to ignore. All right. And
That's a
then
big
students
class.
equals a new string array of size. Remember, dynamic array versus dynamic variable. It's just new in the type or new in the type square bracket size, right? You just add the square brackets and put a size in there, and that creates an array of these things as opposed to just a single one. And I said an array of variables, but if you're working with strings, it's really an array of objects. It's really an array of
That's a
objects.
big, array.
Yeah, it is a big array. And we're going to learn how to make that better eventually. Let's see if I know how to write a for loop. Maybe you remember how to write a for loop. I less than size, always less than size, not less than or equal. And then we're going to say get line.
We forgot your I.
What?
And I equals 0.
You want an I there? Okay. Get line, we're going to get it from CN, and we're going to put it into my students array at location I. If you're going to get input, you should always precede it with an output statement, right? Enter the name of student number, and because we count weirdly I plus 1. And by we, I mean computers, right? Because you're not student 0, you're student 1. Student 1. And then I could output the students. So see how the students are. And then I get to write another loop that looks exactly the same. Actually, slightly different. I less than size. I'm going to do the comma separated trick. So go size -1. Right, see out, right, students at I, and a comma. And then at the end, we'll see out students at size -1. And because the last student is always located at what? Size -1. I wrote that a lot, or quickly, but that's because guess what? Everything I just highlighted is not new, right? It's old.
It's old news.
I mean, it would be better if it was an unsigned integer because then it could be a little bit bigger, but it's not going to change. Unless they put in a negative size, which then you would can't do on that. Even if it was an unsigned int, you'd want to make sure the size was at least 1. Although an array of size 1 is just a variable, so you kind of want the array to be a size. What's new? Just line 12, right? Students equals new string of size. But once you create a dynamic array, it's just a what? An array. How do I get to values in an array? I use a loop, right? So that's why I have a loop, right? Get line allows me to get, right, a line of input, right? Because someone's name might have that. Let's see if I did it correctly. Nope.
Oof.
No get line, no string. Let's include string, use an std. What? No cn?
Oof.
Comma. Use std cn. I swear I know how to program. How many students?
10?
20.
Yeah, no, 3.
3.
John Doe, Jane Doe,
Billy.
Billy, Joe. And students are what? John Doe, Jane Doe, and Billy Joe. Right? The array got created at runtime based on user input, right? So it became the size that it needed to be, not taking up a bunch of extra memory that we didn't. Right? And then the cool thing is that what? We could have 10 students. I'm not that creative, so there's my students. Right? 10 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So my dynamic array is created while the program is running, and I can basically create it whatever size I'd like it to be. Make sense? Questions there? Okay.
What?
What?
Never mind.
Who? What? Where?
I'm gonna ask if you created an array in a loop. If you could use the array in the loop, and then would the array go away after the loop closed?
No. So we're going to talk about that next class with destroying. But dynamic things don't go away unless you destroy them. So they get allocated from a different place. Everything, all the regular variables get allocated on the stack. All the dynamic stuff gets allocated from the heap, 2 different sets of memory. We're going to talk about it all. And stuff on the stack, right? When a function ends, remember we talked about scope, we talked about scope. Everything on the stack is the reason scope works. And so as functions end, things pop off the stack, and those variables go away. Things allocated over here, they don't care about the stack. So if you didn't get rid of them before the pointers that point to them go away, guess what happens to them? They hang out, right? Taking up memory leaks, right? So we're going to talk about how we can fix all that. Great question. Other questions? All right, let's see if these next slides are even worth it. It's a funny thing to say about your own slides. Yeah, I made them, but maybe we don't care about them. Blah, blah, blah. This is showing that, okay, pointers are types. you can use them anywhere that you use a type, such as the return type, right? So a function can return an integer, it can also return a pointer to an integer. A function can take in an integer and it can also take in a pointer to an integer, because you can use pointers anywhere that you can use any type. Right? So int star is a pointer type, right? Which we've seen today. If you pass in a variable that is a pointer, guess what? It's going to act like call by reference. There's no ampersands there, so that's not called by reference. It's called by what? Value, right? But called by pointer, right? But right, what does P hold? It holds a memory address, and so if I affect what P is pointing to, it's going to affect other stuff because it's holding a memory. All right. So it's going to act like call by reference, even though it's not actually.
So technically, if you put a pointer in the function, like it accepts a pointer, can't you just change it outside the function and just completely mess it up?
Yep. Because it exists outside of scope.
Like you can just point to somewhere else, and then you can just.
Yep. Right. So in this example, in main, I have my variable value of 5. We have P as a pointer, points to my var. And then when I call the function, I pass in P, which is a memory address. So point gets the value that P stores, and the value that P stores is really my var's memory address. And so when I say star point gets assigned 10, 10 doesn't go into point because I dereferenced it. It goes into what point is? Pointing to. Good. And point is pointing to the same thing that P is pointing to, which is pointing to my var. And so what changes? My var. Okay. So my var, which is in main, a totally different scope. Agreed? My var is in a totally different scope. It gets changed in a different function because that pointer holds the memory address of that. And that's how call by value works, right? Call by value doesn't hold the value, it holds the memory address of the variable. So this is doing the same thing except using pointers as opposed to ampersand.
Interesting.
But you can use pointers, right? Pointers anywhere that you can use regular variables.
What happens if you got the ampersand on now there?
Compiler. Because int star P is type, the type is int star. The type of my var is int, and they'll say, right, problem assigning int and int star. So I'll show you that error message real quick, and then you guys should probably get working on stuff.
Yeah.
Which is important. I'm gonna ditch you for a little while. I have a meeting at 10, so you're gonna be on your lonesome selves. But today's lab's not too hard, so that's good. So if I said int star, or let's see, int x, right? And I said int star P equals x, right? Let's see what happens. Right? So invalid conversion from what? Int to int star, meaning that, right, it even tells you x was trying to get it assigned into P. P was of type int star, x is of type int. And when C++ doesn't know how to auto type convert for you, then you get error messages about mismatched type. Right? So here, right, you're converting from int to int star. Did it work? It did not. Right? Same thing would happen if you said like double star P equals ampersand x, but x wasn't, oh, x is an integer. Okay? So let's see what happens there. Right? Cannot convert int star to what? Double star. So once again, x was of type int. When I say ampersand x, then it's not of type int, it's of type int star, because it's a memory address of ints. But P is a double star, right? So once again, you can't put non-pointer types into pointer types, and you can't put the wrong pointer type into another pointer type, right? There's a reason why it's int star, right? It's not like something else. Right? Otherwise, we just say this is a pointer pointed to whatever we want. We have to say it's a pointer that points to a specific type. That way you can interpret, right, the bits in that memory address. So they'll have to match it. Questions there? I think you're making arrays today in your lab. Does that sound right? Let's look at it. We're right on lecture 12.
Yeah.
My goodness. You guys are still hanging out in my class too, huh? What's wrong with you? Oh look, ugly unit test. Let's go. Actually, I don't think you're writing functions that, yeah. Okay. So you're writing 4 functions. All these functions are going to work with arrays, but they're going to work with a dynamic array that then you pass, basically I'm going to pass the pointer around. So your first function, make dynamic array, is very important because if you write that one incorrectly, even if you write all your other functions correctly, it's not going to work because I'm going to create a dynamic array with your function, and then I'm going to use that dynamic array in all the other functions. So let's talk about the first one. Line 18 says the return type is what? Int star, right? So what does it return? A pointer, right? A memory address. Okay, what does it take in? Unsigned int for size. Okay? And it says that you should allocate a new array of integers of that size. Right? So allocate memory for a dynamic array of integers, which is why the return type is what? Int star. Okay. When you see the word dynamic, what word's going to have to show up in that function? New, right? So you need to create a new array of the given size, right? And that should be a new array of what type? Integers. Okay. The size doesn't have to be an unsigned int, but if you think about arrays, you can't make negative size arrays, so unsigned int makes more sense for size.
You don't have to do that or check.
Yeah, except for 0, theoretically. But I don't think I'm not making you check for 0. But you should theoretically check for 0, because allocating an array of size 0 is no good. You want your hint on this one? The hint is you can do it in either 1 line or 2 lines. Okay? 1 line if you realize that you don't actually have to create the pointer, because the pointer is what gets returned. Okay? 2 if you want to create a pointer, create the array, and then return the pointer. But remember, when you use the word new, what does new become? It becomes the memory address of what you created. Agreed? What is this function supposed to return? A memory address. So you could do it in 1 line if you want, or you could do it in 2 lines. You can do it in 10 lines, but I don't recommend that.
Yeah.
All right, so this might look a little weird, but this should be really easy. And in fact, the hint here is that you already wrote these functions. Remember when you wrote sum and like min and max and all that kind of stuff? Not only did you write it in the lab, you also wrote it in an assignment. Okay. The only difference here is that your array parameter looks just a little bit different, right? Instead of being int the array square brackets, it's int star the array. But we know now that array variables are really pointers to the array. So int star the array, guess what? The array is really a what? Array. So treat it like it's a what? An array. Okay. And then we pass in the size because if you're going to loop through that array, you want to know how big that array is. Agreed? The only weird thing is that it says, everyone sees @throw. It says the message null array reference if the array is null. Okay, so we haven't talked about null as a big, right, all uppercase, but that is a value that you can give pointers, meaning they don't point to anything. Okay, we want to make sure that the array, the pointer is something, it's pointing to somewhere. And so we need to write an if statement to check to make sure that that value is not null. Okay, and it's as simple as doing something like this. Right? If, right, your pointer equals null. Right? Null is a value that exists. So if your pointer equals null, that would mean that you should not use your array because the pointer is null. And in fact, it will crash your program if you try to use the pointer.
All right. Star P, exclamation point. P equivalent to null. Is
No.
not equal.
You don't do the star. Null is a basically 0 for pointers.
I mean, just figure logic's reverse, so you put an exclamation point.
Yeah, you could, right, if you want.
No.
But what I want to happen is I want the program to throw that message, which will end my function if there's an error. So if this is null, then you would say throw, and whatever it is that you want to throw. That will end your function, so you don't have to worry about, right, an else or anything like that. Does that make a little bit of sense? That's the new thing that we haven't seen.
So that's what we check first.
Yes. We check it first because it's the thing to make sure everything's working correctly. Right? Sometimes students, they're like, okay, I'm going to check it, but I'm also going to do stuff with the array above. Well, don't do that, because if this throws an error, right, that's a problem. You don't want to put any code above that. This first, then, right, loop through your array and sum it all together. Or loop through your array and max it all together, or loop through your array and min it. Okay? You've done max, min, sum before, okay, with arrays. But you're doing the exact same thing in this one, you just have a simple if statement to check for a point. Remember, once you create a dynamic array, it's just a what? An array, right? So in your min function, if you want to work with that array, you're going to say the array square bracket 0, the array square bracket I, if you're in a loop. Right? Don't try to add stars or anything special in those functions because they're just arrays. And did you know about stars before today? No. So don't use them when you're looping through your array because you didn't use them before today. You don't need them today when you're working with arrays. Does that make sense? Questions? Okay. So get cracking on that. You'll have more, or we'll do more with pointers on Monday. And then I'm not going to lecture about them anymore, but we're going to use them the rest of the semester. Which sounds like so much fun, right?
Yeah, go all the way down. All the way down. Who's there? Press enter. Yeah, that's all I wanted to, yeah. But yeah, that's pretty much what I want.
We got to take it. We're making
So that's right. But you need to get out. So you just return that one. And your array. And then you know what's easy. That's an array.
you already got.
Sounds like activation here.
Sounds like activation deletion. Especially since model worker comes up next week. Who's the group still hanging out?
I do. Okay.
We didn't do it today.
Yeah. I don't know if this is working right now. Yeah. But it's only when I actually get rid of everything won't run. It literally won't even run. And now it's telling me it's stuck.
It's already moving. You better get a lesson.
Yeah, although we never really ever did assignment and return on the same line, so you just don't need to do it. So get rid of the int star equals. And we'll talk about what's happening. So
Does it-
new int dynamically allocates this array, and it becomes that memory address. So you return that memory address, which is the next memory. And then,
Because
and
the
then
function is
yeah.
pointer, then whatever it returns is just automatically.
Exactly. And then on my side of things, I'm going to take that pointer and store it somewhere. And that memory address and store it somewhere.
Hey, I did that correctly.
Well, I mean, yeah, you got some, right?
I actually.
Right? Just like a regular. And so you'll return A, right? That makes sense?
Yeah. For, line 11, I was looking at, since there is like two, variables, like dollars underscore, since I'm sure, would the, amount one dot, dollar underscore slash amount.
I wrote that function for you. Yeah, so there's no read line. I wrote the plus for you. Your goal line.
No, pointer?
Well, it's just a pointer, right? It's not the array, it doesn't matter. If that pointer is wrong.
Oh, I see.
And then memory address is actually going to be from this. And then, yeah. Well, no. So if you're gonna do that, you would return the array. But you can also, if you want to do it, you have to realize that new int, new is always going to be new int array size creates an array, it becomes the memory address. Now on my side of things, right in main or wherever, I'm going to take that memory address. But you don't have to give your name, so I just want to go yeah, it's exception handling, which we're not really talking about yet. But it's a way to like run code and then catch errors and do stuff with it.
Oh. I thought you were doing like a word for CL.
No, it's a real thing that I'm not going to talk about.
So CL are our thing.
Right? Yeah. CL is a CL throw. If you don't catch a throw, it crashes your program. Or you can catch a throw and then you can handle errors gracefully. So I don't know if you've heard of like try catch stuff before, but they're all try catch throw are all the same.
It's kind of like Sanger, but you do more with it.
Yeah, I know that's if you tell, like in your documentation, you say, oh, this function throws an error on whatever, then when someone uses your function, then they'll put it in a try catch and deal with, okay, if it throws an error, how do I want to handle that? When programs get complicated, you need this exception handling. No. I just added more due date. This is in the due date. It's all the same, right? Yeah, wait. It's got enough to do UI, to do list, to do item. Yeah. Yeah, my unit test will test your list and item, right? Yeah. Yeah, perfect. That's it. Okay, that means that you understand a little bit of what I'm saying. That's good. Yeah, that looks scary, right?
Yeah, I was gonna say that too. So you see how it did 5, and it should have printed it out. Okay, 6. There's just so many photos that I have probably myself to share. Yeah, probably. There'd be some.
Good news, maybe it's not till Monday. Monday, the power went out. Yeah, right, everything's all backed up. My whole life's been. Nope, because you don't want to, right, this is like haircut. You always want to do your haircut before you do it.
Do I
Yeah.
see that?
Okay.
Okay.
So if we were, annual, that's $1,000 equals, minus $1,000, something in subtraction would be opposite.
Well, you have to understand what it's doing before you just start replacing plus signs. So, the big key to look at in this one is that if I have two money objects, and they're both made up of integer dollars and integer cents, because this one's made up of integer dollars and integer cents. To add them together, I can't just add the dollars and the cents together, right? I need to get them into one unit and then add them together,
Yeah.
and then break them up. So that's what the code's doing. So read the comments, read the code. And that's how it points to the right there.
7. If we're doing checks on a loop, we have to make these on assignments, right? Because we're
Yes.
So would I have to make the assignment here? Would that have to be an assignment? Because I'm assignment to that. Oh, you're
No, the array is integer, yeah.
Oh, it is.
I did this for you. No, I can't do this, but that's what you want, right? Confused by the allocation.
Yeah, so just, well, because
That's, I don't work on this.
I don't know why I'm supposed to do that.
I have no idea.
So, fine, so, yeah, so, we also. Okay, so, yeah. So,
I think what I did is I had to move it because you basically do the same thing I did, but on.
You just stay on one line.
Yeah, because like it's already telling me that this one thing.
Not really that good. I mean, it's a time theory class, so it's not as much as like the trading class, but.
Yeah, exactly. So it's a pointer, but it's just it's an That's also
I'm not sure if I'm doing this correctly. So I wrote an if statement to check to see if that pointer is null. And I did that, and those tests are failing.
Because it wants you to be, you want to throw null array reference. I'm checking for that specific word, all uppercase.
Oh, so you want me to type that in here?
No. In the string should be null array reference.
Oh, okay.
All capital.
I'll do that. So I did it right. It's just that
You did it right.
Yeah.
You just threw the wrong message.
Okay.
Yeah, you could ask me on that.
You throw, it's not gonna return the real false. It might circumvent.
When do you want to use them all?
No, I mean, like your create that function sum, so the end that you're returning into sum. So that's fair. Yeah, right.
Oh, right.
The thing that you did all the effort to create and do, and
Yeah.
that one.
Is that what that word, is that how that works?
I'm not sure, it's basically, this, I can't talk, this slide will let you say when you want, so there's like,
Right, well, I'm saying you guys are here, but what I will say is that what I did for that, at least I was fine, I completed it. Basically, how I read it, all it wants you to do is basically take this number and make it revert and so if it's negative, that's what this gets called, and then it'll make it positive. Multiply by negative one. I don't know what it's gonna work because I can't compile it, so I haven't finished my last upgrade. Yeah, it's just maybe a variable dollars, maybe. I just made it variable. I don't know what that looks like, but it just, that's what I got so far. I haven't finished this part, so.
we actually have variables to use, here.
Yeah, so what I did is for that, so basically it is dollars, yeah, exactly. And then I store that into whatever that answer is in the bar, and then that's what I return. So the sense of, I don't know, because I can't file it, because I can't add it. I'm almost done with filter, so that should be good. Well, I'm having to move some of this stuff. 80. So this is good. I don't think it's safe. It's supposed to. Spaces.
Now, it's important. Yeah, sorry. Actually, it's around 11. I'm not sure.
It's all.
Today is.
Yeah, today is
That's
not.
not fine. I thought I finished this days. I just finished this, or,